Today's explanation is for the crystal field theory, which explains what color a complex is going to be. Okay, or tentatively, how can you determine roughly what color a complex is going to be? Now, this, let's say, is the central metal atom. I have defined the three axes, the x, the y, and the z, using these bonds here. The way d orbitals are arranged, dxy are arranged like this. They are a double dumbbell. dxz would be arranged like this, which is between the axes. The exception being dx square minus y square and dz square. They are oriented along the axes. So now, when this metal is not bonding with anything, the electron density around it, electric field around it, is going to be symmetrical because there's no particular preference as to which axis is where. So you can imagine it being, rotating very fast in 3 dimensions, and the entire probability density just looks uniform. That is, these are degenerate orbitals. They have the same energy. So anything could be oriented in any direction. But once the electron density of a ligand starts to approach, I am specifically referring to octahedral complexes. When it starts to approach, this degeneracy of the orbitals is lost because the orbitals which are oriented between the axes are not facing the electron density head on. Whereas dx square minus y square and dz square are facing the electron density directly, leading to destabilization. Okay, so these two orbitals, the ones that are oriented along the axis, increase in energy with respect to the degenerate zero original energy of these orbitals. But now we are not providing any additional energy to the system, so there has to be some relative stabilization as well. So the other 3 orbitals which are oriented between the axes become stabilized. So essentially the 5 orbitals split into 2 groups. 2 of them become higher energy and 3 become lower energy. These are called T to G, as in T, 2 and G, and these 2 are called EG. So these 2 get destabilized and these 3 get stabilized. Now if the net energy of the system has to remain constant, the extent of destabilization and stabilization have to match, which means the destabilization is 0.6 times of the split between the 2, and stabilization is 0.5 times the split for each orbital. So that these 3 add up to 12, and that 2 adds up to 12 as well. Or you can think of it as 2 by 5 and 3 by 5. Okay. Now this split that is caused by the ligand, that is, how strong is the electric field which is causing distortion, is what decides the magnitude of split between these orbitals. The stronger the field, the larger the split. The larger the split, the more energy will be required to excite electrons from T to G to EG. Okay, this excitation is required for the complexes to be colored, and as a result, this split is the one which decides what color the complex is going to be. So if it's a strong field ligand, the split would be large, which means lower wavelengths, which are the higher energy radiations, will get absorbed, and as a consequence, the complementary color would be visible. For example, iron ferricyanide, potassium ferricyanide, KFe, K3FeCN6. Yeah. So in that, cyanide is a very strong field ligand. When it approaches Fe, it splits the complex, it splits the energy between the T to G and EG orbitals to a very large extent. So blue wavelength is absorbed, and as a result, potassium ferricyanide appears blood red. The complementary color would be visible.